In this video, we will learn how to derive the distribution of a random variable like random variable y in this case, which is a deterministic function of another random variable x whose distribution is known. As long as this deterministic function g is strictly monotone on the support of the random variable x, we are guaranteed to be able to derive the distribution of our random variable y. Later in the video, we will soften the condition imposed on the function g so that even functions that are not strictly monotone on the entire support of the random variable x will work for us, as long as they are piecewise strictly monotone on the entire support of the random variable x. Okay, that's the mission in this video. Let's get going. Okay, so we said that we have a random variable x with a known CDF, and we form random variable y by applying a deterministic function g to the known random variable x. But what is a deterministic function? In particular, what does that word deterministic mean? Let's focus on that for a moment. Okay, so what does it mean for our four random variables here, c, I, d, and r, to be deterministic functions of the random variable f? That means that f is the only source of randomness for these random variables. As soon as the random variable f is realized, as soon as it takes on a value, these four random variables will immediately have a value as well. There is no source of randomness for them outside of f. They have no personality outside of f. They immediately fall in line. Let's contrast our four random variables, which are deterministic functions of f, with the following two random variables, which are not simple deterministic functions of f. Suppose f gets a realized value, suppose of 72. Notice that z1 and z2 do not immediately get a value. z1 here is a random variable that is drawn from the normal distribution with a mean of f and a variance of 9. As soon as f is materialized, experiment 1 is finished, so to speak, but in order for z1 to get a value, a second experiment needs to be realized. So once f takes on a value, 72 in this case, then z1 now can be conceptualized as being sampled from the normal distribution with a mean of 72 and variance of 9. And when the second experiment is realized, let's say that we get a value of 74. And same for z2. z2 does not immediately realize its value as soon as f is realized, because z2 consists of an additional experiment on top of the experiment that will materialize f. In this case, z2 is taken to be the sum of f dice. So until f is realized, we don't know how many dice we have to roll. Once f takes on the value 72, now we're ready to roll our 72 dice, and suppose that we get 80 for the sum of 72 dice. The point that I want to make clear here is that z1 and z2 have a personality outside of f. In other words, f is not the only source of randomness for these two random variables. F is only part of the story of z1 and z2. Okay, so imagine that we have a random variable x with a known distribution, with a known CDF. And now we form a new random variable y by applying to x a deterministic function g. So y is equal to g of x. The question is, what is the distribution, what is the CDF of the new random variable y? As you can probably already guess, whether or not we can derive the distribution of y in terms of the distribution of x will depend on the nature of that deterministic function g. So let's develop a methodical approach here where we will ask three questions. The first question we will ask is whether g is a function on the range of x. The second question we will ask is whether g is a one-to-one function on the range of x. And the third question we'll ask is whether g is a strictly monotone function on the range of x. A strictly monotone function is automatically 1-to-1, so that third question is asking for something more than the second question. Each of these three questions are getting to a characteristic of G that gives us some powers. And let's turn on these powers one at a time so that we can isolate the effect of each in turn. So in example 1, let's look at a transformation G that is not even a function. In example 2, we'll look at a transformation G that is a function but not 1-to-1. In example 3, we'll look at a transformation G that is a 1-to-1 function but not a strictly monotone function. And finally, in example 4, we'll look at transformation G that has all these three powers turned on. It's a function, it's a 1-to-1 function, and a strictly monotone one. And we'll see how that will then allow us to derive the distribution of y, having knowledge only of the distribution of x and of that transformation G. Okay, so here's example 1. Imagine that we're a small manufacturing firm, and we have some government entity come over, and they're going to do some inspection to check on the incidence of defective items. And they'll do so by sampling randomly 10 units from our assembly line, and for each unit they will determine if it's acceptable or defective, and then they will count the number of defective units in this sample of 10. Then we have our random variable x here as the number of defective units. Since the interest of this inspection team is surgically on just the number of defective items, notice how elegant it is to work now with random variable x as opposed to the original sample space. The original sample space has 2 to the power of 10 outcomes. It's overwhelming. But the range of random variable x has only 11 elements, integers 0 through 10. This inspection team cares only about the number of defective items. Suppose that in the sample of 10 units, there's one defective item. The inspection team doesn't care if that defective item occurred on unit 1, unit 2, unit 9, or unit 10. They only care about the number of defective units. So we created this random variable x by discarding a lot of information that we have no use for here. And we kept only the information we need, the number of defective items. Now suppose that this inspection team will then apply a penalty based on the number of defective items. Notice, however, that if there are 9 defective items, no penalty is specified. And if there are 8 defective items, the penalty is either 25,000 or 16,000. So we can think of calculating the penalty y by applying a transformation lowercase g to x. But notice that that transformation lowercase g is not even a function because, first of all, there's an element in the range of x, 9, which is not mapped to any value in the range of y. So the totality property of a function is not satisfied. And on top of that, for element 8 in the range of x, notice that it is mapped to 2 different values in the range of y, and so the well-definedness property of a function is also violated. So we have 2 reasons now to say that this transformation lowercase g is not a proper function. Because y is not a function, y is not a random variable. So we cannot ask any questions about y. We cannot ask what the probability of y taking on the value 9,000 is, or what is the probability that y is less than or equal to 9,000. Y is not a random variable, so none of these questions make sense. Okay, let's have a look at a slightly more interesting example now. In example 2, everything up to creating random variable x stays the same, but we've changed the transformation lowercase g used to obtain the random variable y from random variable x. Now this transformation lowercase g is actually a function on the range of random variable x. Why is that? No value in the range of x is mapped to 2 or more y values. And there is no value in the range of x that is not mapped to any value in the range of y. So the two properties of a function are satisfied. Y is a proper function. If you recall from my video on random variables, there's some additional conditions now to take y from being just a function on the range of x to it being a valid random variable. Measurability would come in there, but we don't want to open that box now. Let's point out one thing, that when x takes on the value 10 or 0, both of those values, 10 and 0, are mapped to the exact same value of y. We will later say that such a function g is not one-to-one on the support of random variable x, but it is perfectly fine as a function, right? And as of now, we're only asking if g is a function, and it is a function. Therefore, we can now ask some questions of a random variable y. We can ask, what is the probability that y takes on the value 9,000? And because y is just a deterministic transformation of random variable x, that question can be rephrased in terms of x. Well, y takes on the value 9,000 only when x takes on the value 2 or 8. So whatever that probability is, whatever the probability of x taking on the value 2 or 8, that's the probability we're interested in. Now recall that we know the CDF of random variable x, so we could work out what the probability of x taking on the value 2 or 8 is. And we can ask a question such as, what is the probability that our random variable y takes on a value less than or equal to 9,000? But now answering this question is tedious, because we would literally have to trace back each value in the range of y that is less than or equal than 9,000 and see what values in the range of x mapped to those. Wouldn't it be nice to have an answer that is also in terms of an interval? So when g is a function, but not one-to-one, we'd have to look at the particular example in each case. So very tedious, nothing generalizable. Now in example 3, we turn on one additional power, being 1-to-1. Once more, nothing changed up to the point where we create the random variable x, but now we use a different function g. You can verify for yourself that g is indeed a function. Each value in the range of x is mapped to exactly one value in the range of y. And it is 1-to-1 because no value in the range of y is being mapped by two or more values in the range of x. Like before, we can ask a question such as, what is the probability that a random variable y takes on a particular value such as 9,000? And we would just have to map back from 9,000 to what value of x was it that mapped to it, and it's x equal 3. So then the probability that y is equal to 9,000 is the probability that x equals 3. Notice that these are not two different events that have the same probability. These are exactly the same event, because if you recall, y has no randomness outside of x. Y is just x with window dressing. So if we're asking a question in terms of y, what's the probability y is equal to 9,000? Well, we just undo that window dressing, and it's the probability that x equals 3. Those two are exactly the same event, not just different events that happen to have the same probability. Notice that the second question pertaining to the probability of the event that y is less than or equal than 9,000 is about as tedious as before. We still have to identify all the values in the range of y satisfying this inequality, and then we have to trace them back to the values in the range of x that mapped there. What we get from knowledge of g being a one-to-one function is that when we are translating an event in terms of y back to an event in terms of x, for each individual value of y, there will be exactly one value of x. If you recall in example 2, for the probability of y equal 9,000, there we found that it was equal to the probability of x taking on the value either 2 or 8. So one value of y mapped back to two values of x. But now, because we have a one-to-one function g, one value of y, we can be certain it will map back to exactly one value of x. So all in all, knowledge that the function g is one-to-one helps us with inverting single-valued events, but it doesn't help that much with inverting intervals or multi-valued events that are inequalities. Now in example 4a, we finally turn on that last superpower of function g, which comes with it being strictly monotone. If a function is strictly monotone, which has two flavors, strictly increasing or strictly decreasing, then it is automatically also one-to-one. Notice that this function y equals 1000x squared is not strictly increasing on the entire real line from negative infinity to positive infinity, but we don't care about the entire real line. When we apply a function to a random variable, we only care that this function be strictly increasing, in this case, on the support of the random variable x. And in this case, the support of random variable x consists of the integers 0 through 10, and on the integers from 0 to 10, our function is strictly increasing. In plain language, that means that a larger value of x gets mapped to a larger value of y. And you can see that in these neat parallel arrows that we have going from the range of x to the range of y. Like before, we can ask the first question, what's the probability that y equals a particular value such as 9000? We map it back to the range of x. So that's the same as the probability of the event that x is equal to 3. Right? Again, these are identical events. These aren't just events that happen to have the same probability. And on top of that, because a strictly monotone function implies that it is also one-to-one, in our case, our strictly increasing function must also be one-to-one. Therefore, we know that a single valued event in terms of y will map back to a single valued event in terms of x. So we know there's only one value of x that would have mapped to a value of y of 9000. Okay, so far we've described what it is that we get from a one-to-one function. Now let's see what we get from the strict monotonicity. Now we can also answer neatly questions about events in the sigma algebra of y that are intervals. Such as, in this case, we're asking what is the probability that y is less than or equal than 9000? And the answer here is very neat and generalizable, because the way we find this answer is we map back this 9000 from the range of y to the range of x, and then because a strictly increasing function is order preserving, in other words, higher values of x get mapped to higher values of y, the sign is preserved, so y will be less than or equal than 9000 where x is less than or equal than 3. In example 4b, we look at another strictly monotone function, but this one is strictly decreasing. And as you can see here, higher values of x get mapped to lower values of y. And that is true for any two values of x. That's what it means for our function g to be strictly decreasing. So what changes is just that second question now. If we're asking what's the probability that y is less than or equal than 2000, we have to take that value 2000 in the range of y, map it back to the range of x. In this case, a value of 2000 for y maps back to a value of 7 for x. And y will be less than or equal than 2000 where x will be greater than or equal than 7. So notice that the sign has flipped from less than or equal to greater than or equal because our function g is strictly decreasing. But the point is that with a strictly decreasing function, just like with a strictly increasing one, we have a neat and generalizable way of answering questions about intervals. What's the probability that random variable y is less than or equal than 2000? And you can already make the connection in your brain to the fact that knowing the CDF of a random variable y means that we know the probability of all such events where we just replace this 2000 with a lowercase y, which is allowed to travel through the entire range of random variable y. Let's briefly remind ourselves how, given the graph of a transformation G, we can determine if it is a function, if it is one-to-one, and if it is strictly monotone. Now, we will only care whether it is those things on the support of the random variable x, because this transformation G is applied to the random variable x. So let's ask the first question. Is this transformation G plotted here a function? It is not a function on negative infinity to positive infinity because it doesn't pass the vertical line test. You'll recall the vertical line test involves drawing a vertical line at every point and making sure that it intersects the graph at only one point. So if we're asking, is this transformation G a function on the entire real line from negative infinity to positive infinity, the answer is no. But if the support of random variable x is, say, from 0 to positive infinity, then we only care about whether this transformation G is a function on that support from 0 to positive infinity. And on that support, it is indeed a function. What about this other transformation G? Is it a function? Suppose that the support of the random variable x is the interval from 0 to positive infinity. So we ask, is it a function on that support? Yes, it is, because it passes the vertical line test everywhere on that support interval. Okay, but is it one-to-one? It is not, because it does not pass the horizontal line test. And the horizontal line test is very similar, but now we're going to go through the support of the random variable y. And every horizontal line drawn there needs to intersect the graph at exactly one point. So this transformation G is a function, but not one-to-one. Is a function because it passes the vertical line test on the interval from 0 to positive infinity, but it is not one-to-one because it does not pass the horizontal line test on the entire range or support of the random variable y. What about this one? Suppose that the support of the random variable x is the interval between 0 and 1. You'll notice that the function I plotted here, which consists of those three segments, is a function on the interval from 0 to 1 because it passes the vertical line test everywhere in that interval, and it is also a one-to-one function because it also passes the horizontal line test on the range of the random variable y. But it is not a strictly monotone function. It is neither strictly increasing nor strictly decreasing. Now in this final example, we're finally looking at a function that is one-to-one and is also strictly increasing on the interval from 0 to 1. Okay, so far we've looked at several examples, which hopefully are starting to build some intuition as to why we can expect to learn the distribution of a random variable y, which is obtained by applying a function g to a random variable x whose distribution is assumed to be known. And the main takeaway from these exercises should be the following. Knowledge that our function g is one-to-one tells us that a single valued event in terms of the random variable y can be mapped back to a single valued event in terms of the random variable x, which is very promising because we know the distribution of the random variable x and we do not know anything about distribution of random variable y. If we know that our function g is strictly monotone, as we've already discussed, that implies that it is one-to-one, but what strict monotonicity gives us is somewhat of a superpower, because now we can translate very neatly interval events in terms of the random variable y into interval events in terms of the random variable x. And now it seems intuitively within reach why it is possible for us to learn the CDF of random variable y given knowledge of the CDF of the random variable x and of the function g, in the special case when this function g happens to be strictly monotone. Okay, now the plan for the rest of the lecture is threefold. First, we will introduce the theory that we've just discussed, but we'll do so more formally. This will include defining the preimage operator and seeing the inverse of a function as a special case of that preimage operator, formally defining what it means for a function to be strictly monotone, and understanding when we can use the derivative of a function to determine whether that function is strictly monotone or not. Second, we will cover some of the examples covered in the book to get some practice with these concepts. And third, we'll work through a case study that I've created involving the Artemis 2 mission and 4 questions that the astronauts are looking to answer. Let's introduce the preimage operator. The function g most directly gives us a way of mapping values in the support of the random variable x to values in the support of the random variable y. And because any set of values is just a collection of values, this function g effectively gives us a way of mapping sets in the sigma algebra of x to sets in the sigma algebra of y. So this is what our function g gives us. Now, what if we went backwards? What if we started with this set of interest on the right in the sigma algebra of y, and we were asking what set in the sigma algebra of x maps there? The answer to this question is given by what's called the preimage operator, denoted with lowercase g with a superscript of -1. And notice that the preimage operator takes sets in the sigma algebra of y and maps them back to sets in the sigma algebra of x. But what if our question of interest concerns not sets, but points? So suppose that there's just value lowercase y that we want to map back. A value can still map back to a set. So the preimage of a value in the support of the random variable y may still very well be a set. In fact, we've seen that to be the case when the function g was not one-to-one. If the function g is one-to-one, then the preimage of any value lowercase y in the support of the random variable y will be single valued. In other words, it'll be just a value and not a set. So associated with the function g is the preimage operator. If the function g is one-to-one, then the preimage operator associated with this function is a function, which we'll call the inverse of the function g. But we still need to address one thing. The question is, can we pick a value in the support of the random variable y such that no values in the support of random variable x map to it? Because if that's the case, then this inverse, g inverse, isn't a function, because there would be values in the support of y that are not mapped to anything in the support of x. I brought in an excerpt from the book in which the authors introduce the definition of the support set of the random variable x and the support set of the random variable y. To start with, notice that the support set of the random variable x is taken to consist of all the values of x, lowercase x, where the PDF is greater than 0. Now the support of random variable y, denoted with that capital cursive y, consists of all the values lowercase y such that there is at least one value lowercase x in the support of random variable x that maps there. Therefore, by definition, there is no value in the support of y that cannot be mapped back to a value in the support of x. If the function g is one-to-one, then the preimage operator associated with this function is a function, which we'll call the inverse of the function g. Let us briefly observe a strictly increasing function. Here's our x-axis, our y-axis, and let's pick our strictly increasing function to look like this. This is y equals g of x. For a strictly increasing function, if we were to pick two values, of x, say we have x0 and x1 as such, where we picked x0 to be strictly less than x1, when these values are mapped into our function g of x, g of x0 and g of x1 will respect the same order that x0 and x1 respected. So if x0 was strictly less than x1, then now g of x0 will be strictly less than g of x1. That's what a strictly increasing function does. It preserves the order. If a function is strictly increasing, then it is order preserving. We can think of a function as a transportation company between the domain and the range. It takes points in the domain and it transports them to the range. And the order preserving property of a strictly increasing function means that for any two values that we pick in the domain, like the blue and the green dots here, when they arrive at the destination in the range, they'll be in the same order. The blue dot will still be ahead of the green dot, will be greater than the green dot. And if you look at the bottom, nothing says that the blue dot has to be called x2, right, like we did in the case above. So in the bottom case, we're just calling the blue dot x1 and the green one x2. And the order preservation property means that in the range of the function, the blue dot will still be ahead of the green dot. I duplicated each of these two expressions, and that is because I want to show that the strict inequality implies the weak inequality. So if we were to take x1 to equal x2, then that just means the blue dot and the green dot will be one and the same. Then g of x1 will also equal g of x2. So the strict inequality implies the weak inequality. And that is also the case for the bottom case here. So the question we want to explore is whether for a strictly increasing function g, knowledge that g of x1 is less than or equal than g of x2, whether that implies that the order of x1 and x2 must be the same in the domain. And we'll prove this by contradiction. So let's establish what it is that we know. We know g is strictly increasing, and we know that g of x1 is less than or equal than g of x2. Okay, so for a proof by contradiction, then we would assume the opposite of what we hope to be true. So then we would assume that x1 is strictly greater than x2. But if x1 is strictly greater than x2, by that third statement on the left, that must imply that g of x1 is strictly greater than g of x2, right? Because g is a strictly increasing function, and strictly increasing functions are order preserving. Then we see that we have reached a contradiction, because g of x1 cannot be at the same time greater than g of x2 and less than or equal than g of x2. Therefore, what we assumed must be incorrect, right? And we assumed, this is what we assumed. We assumed that x1 is greater than x2. Therefore, we have shown that it must be the case that x1 is less than or equal than x2 whenever g of x1 is less than or equal than g of x2. We have shown that a strictly increasing function is not only order preserving, but also order reflecting. Notice that if we were to combine these two statements here, we could now write that for a strictly increasing function, we have an if and only if condition. x1 is less than or equal than x2 if and only if g of x1 is less than or equal than g of x2. This if and only if condition could be taken as a definition of a strictly increasing function. But for our purposes, it will actually be just that order reflection, that reverse direction, that will play the biggest role. What we have shown is that if g is strictly increasing, then it is not only order preserving, but also order reflecting. Another way to think about that order reflecting part of g is in terms of the inverse of the function g being order preserving as well. So if all we know about our function g is that it is 1 to 1, then we know that its inverse is a function. But if we additionally know that our function g is strictly increasing, then we also know that its inverse is order preserving. It's not just a function, but an order preserving function. We mentioned that this if and only if statement can be taken as the definition of a strictly increasing function. Let's briefly differentiate it from a non-decreasing function. For a non-decreasing function, if x1 is strictly less than x2, that implies that this function will map to g of x1 and g of x2, and these will be such that g of x1 is allowed to be strictly less, but also equal to g of x2. So it's non-decreasing because it's weaker. We can pick x1 strictly less than x2, but g of x1 may equal g of x2. That's not allowed in a strictly increasing function. And notice that this statement now implies its kind of weaker form, where we put an equal sign here on the left. And nothing changes on the right, because when x1 is equal to x2, g of x1 will be equal to g of x2, but that was already in there. This statement at the bottom that we boxed can be taken as the definition of a non-decreasing function g. And notice that it is weaker than the one for the strictly increasing function g. Because for the non-decreasing function, there's only the if direction, but for the strictly increasing, there's the reverse direction. It's an if and only if statement. So that reverse direction is the key differentiating factor between a strictly increasing function and a function that's merely non-decreasing. We already mentioned several times the special case when the function g is strictly increasing. But given a candidate function g, how do we determine if it is strictly increasing or not? The strict definition of a strictly increasing function is an order statement. Whenever one input is larger than another, the corresponding output is also larger. This definition does not mention derivatives. It is purely about comparing pairs of points. However, in practice, we will most often establish whether a function is strictly increasing by studying its first derivative. However, we have to be very careful here, because if a function g is continuous on the closed interval ab, and it is differentiable on the open interval ab, and the derivative of g is positive, strictly positive, for every value in the open interval ab, then g is strictly increasing on the closed interval ab. However, the converse is not true. In other words, we can find a function g, and we'll look at one of these in a moment, that is strictly increasing, but whose derivative is not strictly greater than 0 everywhere on the interval in question. So we'll say that this derivative greater than 0 business is a sufficient condition for a function to be strictly increasing, but it is not a necessary condition. Okay, so we want to prove that if the left side is true, then the right side must be true. And we already mentioned that the converse is not true. Okay, so how do we prove this? This proof is a direct application of the mean value theorem from calculus. The mean value theorem says that given a closed interval AB, on which the function g is continuous, and given knowledge that this function g is differentiable on the open interval ab, then there is at least one point on the graph in this interval ab where the slope of the tangent line to the curve ab is the same as the slope of the secant line ab. Right, so let's say this again, where the slope of the tangent line is the same as the slope of the secant line ab. So what is the slope of the secant line ab? Let's start with that. Well, the slope of the secant line AB is just rise over run. So it is just g of b minus g over a divided by b minus a. Okay, And then what is the slope of the tangent line? Well, the tangent we're referring to here is the tangent to the curve AB, right? So at every point you can visualize a tangent. So the mean value theorem says that there must be a point C here such that the slope at that point is equal to the slope of the secant line AB. So if we were to write this out, the mean value theorem says that there is a value C here in the interval AB such that the slope of the tangent to the curve given by G prime evaluated at C will be equal to the slope of the secant. This statement is a direct application of the mean value theorem. But now notice that we know that the derivative of G is strictly greater than 0 for every point in the closed interval AB. Therefore, the derivative evaluated at C must also be greater than 0. In other words, G prime C must be greater than 0. Right, so that implies then that this ratio here will be strictly greater than 0. And when is a fraction greater than 0? When both the numerator and the denominator have the same sign, either both positive or both negative. In this case, we've taken b to be greater than a based on the graph, so that would imply then that g of b must be greater than g of a. Okay, so if this fraction is positive and we know that b is greater than a, we know the denominator is positive, therefore the numerator must also be positive, so g of b must be strictly greater than g of a. And if we were to draw this a little differently with b less than a, then again, in order for this fraction to be positive, the sign of the numerator and the denominator would have to be the same. So if b is less than a, then b minus a is negative in the denominator, so we would need the numerator to be negative as well, which means that g of b would have to be strictly less than g of a. And notice that what we've just written down here below the line at the very bottom is exactly what it means for a function g to be strictly increasing. And this completes our proof. We've shown that the left side implies the right side. We've shown that if the derivative is strictly positive everywhere in the closed interval ab, then the function g is strictly increasing on this closed interval ab. We mentioned that the converse is not true. If we know that a function is strictly increasing on a closed interval ab, that does not imply that its first derivative will be strictly greater than 0 on that closed interval ab. As an example, take the function g of x equal to x cubed. This function is strictly increasing everywhere on the real line from negative infinity to positive infinity. But if we were to look at its first derivative, so the derivative of x cubed is 3x squared, and 3x squared is not strictly greater than 0 everywhere, because for x equals 0, g prime of 0 is equal to 0. So here's a function that is strictly increasing on the real line, but its first derivative is not strictly greater than 0 on the entire real line. But notice that even in this case, because we have a function g that is differentiable and it is strictly increasing, then its derivative is greater than or equal to 0 for every point. So that derivative equal to 0 part is what threw off the converse and made the converse not true, but this softer version does hold. In other words, if g is strictly increasing on its domain, it doesn't mean that its derivative will be strictly positive on that domain. However, we do know that its first derivative will be greater than or equal to 0 on its domain. We are now finally ready to derive the CDF and the PDF of the random variable y for the special case when g is a strictly increasing function. So how do we do that? We write what the CDF of y is by definition, which is the probability that capital Y is less than or equal than lowercase y, where this lowercase y can be thought of as traveling through the entire range of the random variable capital Y. Okay, but we said that y is just a deterministic function of the random variable x, therefore the probabilistic behavior of y can be described in terms of that of x. Right? Recall that y has no source of randomness outside of x. When the experiment is realized, x will get a value as soon as x gets a value, y gets a value immediately, right? So we can just replace y with g of capital X. And let's again remind ourselves that these two events that I numbered here aren't just distinct events that happen to have the same probability, they are exactly the same event. Because the randomness of y comes exclusively from x. Okay? Now, notice that g of capital X and lowercase y both live in the range of y. And this g of capital of X less than or equal than y is an event in the sigma algebra of y. But we don't know anything about the probabilities of events in the sigma algebra of y. But we do know the CDF of random variable x and the probability of events in the sigma algebra of x. So then we want to translate g of capital X and y from the range of y to the range of x. And we happen to know that g is a strictly increasing function, and that means a lot of things, but what we care about is the fact that it means that the g inverse is a function that is order preserving. So if we take two values in the range of y in a certain order and we transport them from the range of y to the range of x with the function g inverse, when they arrive in the range of x, they'll be in the same order that they were in when they departed the range of y. Okay, so let's do that. Let's apply g inverse to both sides. And now the sign is preserved because g is a strictly increasing function, and hence g inverse is order preserving. Okay, now let's take a look at the left side here. So imagine that we have a value in the range of x that is given by this random variable x. When we apply the function g to it, it will travel from the range of x to the range of y. And when it arrives to the range of y, it will be g of capital X. Now, if we then apply g inverse to it, then this value will travel back to where it started. So this right here is g inverse of g of x. But that's the same thing as x. So what we have on the left side is just x, and what we have on the right side is g inverse of lowercase y. But now we recognize this as the CDF of x evaluated at the value g inverse of lowercase y. And there we have it. We have derived the CDF of random variable y in terms of the CDF of random variable x and the inverse of the function g. And if we were after the PDF of the random variable y, well, we can get that by taking the derivative of the CDF. So the PDF of the random variable y is just the derivative of the CDF of the random variable of y. And then now let's replace the CDF of y with the derived value in terms of the CDF of x. And now we apply the chain rule, and the derivative of the CDF of x evaluated somewhere is the PDF of x evaluated somewhere. And now by the chain rule, we'll also have to take the derivative of the argument, which will be d dy of g inverse of y. We now have an expression for the PDF of y in terms of the PDF of x. Let's look at exercise 2.1, part A. Here we're given the PDF of a random variable x, and we're given a random variable y as a function of the random variable x. And we're asked to find the PDF of the random variable y. Let's do that, and let's do so by first finding the CDF of the random variable y, and then getting its PDF as the derivative of the CDF. Before we get started with finding the PDF of y, let's try to establish whether the random variable y is a strictly increasing function of x. Our random variable y is the function g of x, and in this case it's x cubed. So in other words, the function we're dealing with here is g of lowercase x is x cubed. Okay, let's explore its derivative. G prime of x is equal to 3x squared. Notice that this expression 3x squared is not strictly greater than 0 on the entire real line from negative infinity to positive infinity. But fortunately, we do not care that it be strictly greater than 0 on the entire real line. We only care that it be so on the support of the random variable x, which in this case is the open interval between 0 and 1. And indeed, this expression 3x squared is strictly greater than 0 on the open interval between 0 and 1. Okay, so we're in business then, because that means that g of x is strictly increasing. Now that we know that g of x is strictly increasing, we can find the CDF of y. So what is the CDF of y? It's the probability that capital Y is less than or equal than lowercase y. By definition, then we replace capital Y with x cubed. Okay. Now, x cubed and lowercase y are both values in the range of the random variable y, and we want to transport them back to the range of random variable x. And we will do so by means of the inverse function. So what is the inverse function? Well, let's take a look. G of x is x cubed. In other words, y is equal to x cubed. Now we just need to solve this for x. And we have that x is equal to y to the power 1/3. And this is our inverse function, g inverse of lowercase y. That's our inverse function. And now we can apply this inverse function to x cubed and y to take them back to the range of x. Okay, so let's do that. The only thing left is to put the sign in there between these two expressions, and because g is strictly increasing, g inverse is order preserving, and therefore the sign will be less than or equal, same as it was here on the left. Okay, and now let's replace g inverse with its actual value of y to the power 1/3. So what we have is that the probability of x cubed to the power of 1/3 is less than or equal than y to the power of 1/3. Okay, and then on the left, x cubed to the power 1/3 is just x, no surprise there. This was by design. And this expression is nothing other than the CDF of x evaluated at y to the power 1/3. Okay, and we're done deriving the CDF of y. Now let's obtain the PDF of y as the derivative of the CDF of y. The PDF of y is the derivative, d dy, of the CDF of y, which is the CDF of x evaluated at y to the power 1/3. and the derivative of the CDF of x evaluated somewhere is the PDF of x evaluated there, times, by the chain rule, the derivative of the argument, which is the derivative of y to the power 1/3, which is 1/3 times y to the power of minus 2 over 3. Okay, and now let's plug in the expression for the PDF of x. So we get 42 times, instead of x to the power of 5, we'll have y to the power of 1/3, the whole thing to the power of 5, times 1 minus y to the power of 1/3, times, okay, so we're done with just this expression here, the PDF evaluated y to the power of 1/3. We still have 1/3 left, and we still have y to the power of minus 2 over 3 left. And let's collect some terms here. 42 and 1/3 multiplied will give us 14. Then this expression here will stay as is, 1 minus y to the power 1/3. Okay, and what else do we have? We have y to the power of 5 over 3 times y to the power of minus 2 over 3, which will give us y to the power of 3 over 3, which is just y. Okay, so that's the PDF of y. And what is the support of random variable y? You can see that when we plug in 0 for x, we get 0 for y. And when we plug in 1 for x, we get 1 for y. So the support of y will be the same open interval between 0 and 1. Okay, and now let's briefly show that this PDF does indeed integrate to 1 over its support. So the integral from 0 to 1 of the PDF of y, which is that, okay, so I'll just write here the PDF of y is what? So let's distribute this expression. So we'll have two integrals, integral from 0 to 1 of 14y dy minus integral from 0 to 1 of 14 times y to the power of 4 over 3 dy. The first one will give us 14 over 2 y squared, and the second one will give us 14 times 3 over 7 times y to the power of 7 over 3, the whole thing evaluated from 0 to 1. And when we plug in 1 for y, we get 14 over 2, which is 7, minus 6. And then when we plug in 0 for y, we get 0 minus 0, and the whole thing evaluates to 1. Okay, as expected for any normalized PDF, it should integrate to 1. Okay, so we're done with this exercise. Now let's turn our attention to strictly decreasing functions. And let's do that by first observing what a strictly decreasing function does. So here's our x-axis, our y-axis, and let's take for our strictly decreasing function this function right here, y equals g of x. Knowledge that our function g is strictly decreasing tells us that if we were to pick two values of x, no matter where we pick them in the domain of the function, let's say we picked x0 and x1 here, where we picked x0 to be strictly less than x1, when these values are plugged into our function will map them to values that will reverse the original order. So whatever order x0 and x1 were in, g of x0 and g of x1 will be in the opposite order. So we picked x0 to be strictly less than x1, but notice that g of x0 now is strictly greater than g of x1. That's what a strictly decreasing function does. It reverses the original order. Recall this slide in which we explored what it means for a function g to be strictly increasing, and we derived this if and only if condition. And we've been talking about how If g is strictly increasing, then it is order preserving. So all these signs are preserved as we move from the range of x to the range of y, and from the range of y to the range of x. So now that we will start considering what happens when g is a strictly decreasing function, you'll see that instead of it being order preserving, it will be order reversing. So let's go through these one by one and see what changes when g is strictly decreasing instead of strictly increasing. So if g is strictly decreasing and x1 is strictly less than or equal than x2, then g of x1 will be greater than g of x2. Now, the strict inequality, like before, implies the weak inequality. So this second one is implied by the first one, but we need to change this less than to greater than. So we have that x1 is less than or equal than x2. That implies, given knowledge that g is strictly decreasing, that g of x1 will be greater than or equal than g of x2. And with the third one, if we know that x1 is greater than x2 and g is strictly decreasing, then again the sign will be reversed. So g of x1 will be less than g of x2. And same with the fourth one. We'll reverse this greater into a less than. Here on the right, we've isolated kind of what happens when we travel from the range of random variable y to the range of random variable x. And when g was strictly increasing, the sign was preserved, the order was preserved, but now it will be reversed. So if we know that g of x1 is less than or equal than g of x2, then that implies that x1 will be greater than or equal than x2. And same down here. And recall this slide here where we use the mean value theorem to show that if the derivative of the function g of x is strictly greater than 0 on the closed interval ab, then the function g is strictly increasing on that closed interval ab. In a completely analogous fashion, we could show that if the derivative is strictly less than 0 for all x in the closed interval ab, then that implies that g is strictly decreasing on this closed interval ab. Let's look at an example with a strictly decreasing function g. So in example 214, we have a random variable x that is actually the standard uniform, so it has the known CDF of x. And the support is the open interval between 0 and 1. Okay, and we form a random variable y as g of x, where this function g of x here is negative log. And so now we want to derive the CDF of the random variable y. Okay, so first let's investigate this function g of x that we're dealing with here. So the function g of x we're dealing with here is minus log of x. Let's look at its first derivative. Its first derivative, so is what? Minus the derivative of log of x is 1 over x. And this expression is strictly less than 0 on the support of the random variable x, which is the open interval between 0 and 1. Therefore, our function g is strictly decreasing on the support of the random variable x. And let's find the inverse as well. So this is essentially what we're starting with. Y is equal to minus log of x, and that's the natural log that we're talking about here, right? And so now to find the inverse, we just need to solve it for x. Let's first multiply by minus 1 on both sides. Get that log of x is equal to minus y. Now let's think about what the log of x represents. Log of x is the power to which e must be raised so that we get x. So then in this case, if we raise e to the power of minus y, we should be getting x, right? By definition. And this is our inverse function. Okay, so let's find the CDF of random variable y. The CDF of the random variable y is equal to the probability that capital Y is less than or equal than lowercase y, and that is equal to the probability that minus log of x is less than or equal than lowercase y. Both of these values are in the range of the random variable y. We want to transport them to the range of variable x by applying the inverse function to both of them. So let's do that. And now what is the sign going to be? Well, because g is strictly decreasing, the sign will reverse. And let's just plug in the value for the inverse of g, and what we get is the probability of e to the power minus log of x is greater than or equal than e to the power of minus y. And we can rewrite this as e to the power of log of x greater than or equal than e to the power of minus y. And once more, let's think about what log of x means. Log of x is the power to which e must be raised so that we get x. Okay, so then if we raise e to this power, or log of x, we should be getting x. So again, not surprising. It was by design. We intended to get x here on the left side, and what we have on the right side is e to the power of minus y. Now suppose that the PDF of the random variable x looks like this. And suppose that the value e to the power of minus y is here. Now there are two events of interest here, and I'm going to color the first one with yellow and the second one with orange. The yellow event is the event that the random variable x is greater than or equal than e to the power minus y. The orange event is the event that x is less than or equal than e to the power minus y. Notice that we can be cavalier about the equal part of it. Right? We could erase the equal sign from both sides or bring it back. It makes no difference because x is a continuous random variable, and so the probability of it taking on any one particular value is 0. So we don't have to worry about that. The area under the PDF to the right of the value e to the power minus y gives us the probability that the random variable x will take on a value that's greater than or equal than e to the power minus y. And the area under the PDF of x to the left of the value e to the power minus y gives us the probability that x will take on a value that's less than or equal than e to the power minus y. And we know that the entire area under the PDF must be 1. Therefore, these two probabilities must add up to 1. And notice now that where we left things off here, we were interested in the probability that x is greater than or equal than e to the power minus y. But that can be represented as 1 minus the probability that x is less than or equal than e to the power minus y. And why did we do that? Well, because the probability that x is less than or equal than e to the power minus y is just the CDF of x evaluated at the point e to the power minus y. And then we know what the CDF of x is from above there, and it's just x in this case. So when we plug it in, we just get 1 minus e to the power minus y. And what is the support of the random variable y? It is all positive numbers. Let's have a look at the general case. When g is strictly increasing, what is the PDF of y in terms of the PDF of x? So again, this function g of x here can be written as that. And then if we wanted to find the inverse, would be given by g inverse of y. CDF of y is given by the probability that y is less than or equal than lowercase y, and that's the probability that g of x is less than or equal than lowercase y. Now we apply g inverse to both sides, and because g is strictly increasing, it is order preserving. So what we get is g inverse of g of x less than or equal than g inverse of y. Okay, and on the left side we get just x, and we get this. Okay, and that's just the CDF of x evaluated at g inverse of y. And now the PDF of y is just the derivative of the CDF of y, and the derivative of the CDF of x is the PDF of x evaluated the same place times now the derivative of the argument, which is d dy of g inverse of y. Alright, so this is what we get in general whenever g is a strictly increasing function. Now, what about the case when g is strictly decreasing? When g is strictly decreasing, what is it that changes? We get probability y is less than or equal than lowercase y. It's the probability that g of x is less than or equal than lowercase y. We apply g inverse to both sides, but because g is strictly decreasing, now the order will reverse, so the sign will flip. Okay, so we have probability of g inverse of g of x is greater than or equal, right? We reverse the sign, then g inverse of y. And that is equal to the probability that x is greater than or equal than g inverse of y. And that can be expressed as 1 minus the probability that x is less than or equal than g inverse of y. And that's 1 minus the CDF of x evaluated at g inverse of y. Now to get the PDF of y, we take the derivative of the CDF of y, and the derivative of this is what? So derivative of 1 is just 0. Now we have a minus PDF of x evaluated at the same place times the derivative of the inverse function. Now notice one thing. The PDF of x, which appears up there and down here, will be positive everywhere on the support of x. Now in the top case here, because g is strictly increasing, g inverse is also strictly increasing. Therefore, this d dy of g inverse of y will be greater than or equal to 0. Now in the bottom, because g is strictly decreasing, g inverse is also strictly decreasing. Therefore, this d dy of g inverse y will be less than or equal to 0. But notice that there's a negative sign up front here. And the two negative signs will combine to give us a positive sign. So in both cases, whether g is increasing or g is decreasing, we get an expression that is non-negative. And no surprise there, because this is the expression for the PDF of random variable y, and we know that the PDF of random variable y has to be greater than or 0 everywhere. And it should be strictly greater than 0 over its support. These two results can be combined into one. And you see that down in the book in Theorem 215. Notice what it says. It talks about g being a monotone function. By the way, the book should have been a little bit more precise and call it a strictly monotone function. But notice that it just says basically strictly monotone. It doesn't say strictly increasing or strictly decreasing. because both of those cases have been collapsed into this one formula, where now we have this absolute value on the ddy of the inverse function valued at y, collapsing the two cases. And it works, again, because when g is strictly increasing, g inverse is strictly increasing, and the derivative will be greater than or equal to 0. And the absolute value of a non-negative number is just that number as is. And when g is strictly decreasing, g inverse is also strictly decreasing, and its derivative will be less than or equal to 0. And the absolute value of a number that is less than or equal to 0 will be the positive version of it. This formula doesn't get called by any name in the book, but it is generally referred to as the change of variables formula. It is the formula that is used when we need to derive the PDF of a random variable y, which is a deterministic function of another random variable x whose PDF is known. This formula is important enough that it is worth memorizing, but more importantly, it's important to understand where it comes from. Let's take a look at an example in which the function g of x is not strictly monotone. In this case, our function g of x is x squared, and if we take a look at the derivative of g of x, it is 2x, and now this derivative is less than 0 on the interval from negative infinity to 0. It is exactly 0 for x equal to 0, and it is strictly positive on the interval from 0 to positive infinity. So we said here that the random variable x is a continuous random variable, but we didn't specify its support. If its support is negative infinity to positive infinity, which is what we'll assume, then this function g of x equal to x squared is not strictly monotone on that entire support. It is strictly decreasing from negative infinity to 0, and it is strictly increasing from 0 to positive infinity. We will say that a function like that is not strictly monotone, but is piecewise monotone, because it is strictly monotone on separate pieces which collectively exhaust the entire support of interest. Okay, so let's see how we'll proceed in this case. To start with, things won't change that much. We will try to derive the CDF of the random variable y, and we'll write it as always as the probability that the random variable y is less than or equal than lowercase y, and then we'll replace capital Y with its value in terms of x squared, and this is what we get. The probability that the random variable x squared is less than or equal than lowercase y. Notice that, like before, x squared and y can be thought of as being values in the range of y. X squared isn't a value, but once it's realized, it becomes a value. So previously, when our function g of x was strictly monotone, we knew how to transport these values from the range of y to the range of x. When g of x was strictly increasing, the order was preserved, and when g of x was strictly decreasing, the order was reversed. But now we cannot proceed in that way, because we have no idea how the order in the range of x will be related to the order in the range of y. I plotted here on the right the graph of our function g of x, which is just a parabola. Now, if we draw a line at value of lowercase y here, we can see our question in a new light, because now, effectively, what we're trying to figure out is we're trying to figure out on what interval of x values the graph of x squared is below the yellow line. And notice that that's the case here in the middle. And what is this value over here? That has to be minus square root of y. And what is this value over here? This is square root of y. So then the event x squared is less than or equal than lowercase y is exactly the same event as that of x being between minus square root of y and square root of y. Now notice that the event of interest here, that x is contained between minus square root of y and square root of y, can be expressed as the difference between the green event and the orange event. The green event is the event that x is less than or equal than square root of y, and the orange event is the event that x is less than or equal than minus square root of y. We can write this as the CDF of x evaluated at square root of y minus the CDF of x evaluated at minus square root of y. If we wanted the PDF of y, we would obtain it from the CDF by taking the derivative. The PDF of y is d dy of the CDF of y, which is this difference of two terms. Okay, so we'll take the derivative of each in turn. Let me write it out the long way here. Now the derivative of the CDF of x evaluated somewhere is the PDF of x evaluated in the same place times the derivative of the argument. And the argument is y to the power 1/2. So we get 1/2 times y to the power minus 1/2 minus, and it is completely analogous with the second term. Let's just make one final change. Notice that there is a negative sign there and a negative sign there, which will combine to give this second term a positive sign. These are already exciting times because we're within reach of a very interesting result. But to make it more evident, let us do one more thing. Let us derive the inverse of the function gx on the two intervals where it is strictly monotone. So if we look at the interval from negative infinity to 0, on this interval the function gx is strictly decreasing. Okay, so let's find its inverse here. Well, let's take the square root of both sides, get the square root of y is equal to absolute value of x. And because x here lives on the interval from negative infinity to 0, the absolute value of x will evaluate to minus x. Therefore, we get that x is equal to minus square root of y. And this is the inverse function on this segment. In a completely analogous fashion, we can derive the inverse on the interval from 0 to positive infinity. Again, we start with y is equal to x squared, and that means that square root of y is equal to the absolute value of x, and because x here lives on the interval from 0 to positive infinity, absolute value of x will evaluate to just x, and this is the inverse on this segment. Now this seemed like a good time for me to bring in this part of theorem 2.1.8, which applies to the case when the function gx is not strictly monotone on the entire support of the random variable x. So it applies to our case because here g of x is not strictly monotone on the entire support of the random variable x. And so what this formula gives us is a way to find the PDF of y as a sum of what is essentially the change of variables formula, which we've already looked at. But how many terms will there be in this sum? Well, it depends on how we've partitioned the support of the random variable x. The goal here is to partition it in such a way that on each piece, the function g of x is strictly monotone. So in our case, we've partitioned the support of x into two pieces. The piece from minus infinity to 0 and the piece from 0 to positive infinity. Therefore, in our case, there will be two terms in this summation, so k will effectively equal 2, and I will take on only two values, 1 and 2. So when I takes on the value 1, it will refer to this first term, and when I will take on the value 2, it will refer to the second term. Now if we look a little deeper into this formula, we see that there's the distribution, the PDF of x there, evaluated at the inverse of the function gi. To see this more clearly in our example, let us put a subscript of 1 here and a subscript of 2 there. So now notice that where the PDF of x is evaluated here in this first term, it's evaluated at square root of y, which is the inverse of g1. And if we look at the second term, the PDF of x is evaluated at minus square root of y, which is the inverse of g2. And finally, if we look at the formula once more, we see that there's that absolute value term at the end, and inside the absolute value is the derivative of the inverse of gi. What is the derivative of the inverse of g1? It's the derivative of the square root of y, which is 1/2 times y to the power minus 1/2. Okay, so that's this term here. And finally, this last term here is the absolute value of the derivative of the inverse of g2. In other words, it's the absolute value of the derivative of minus square root of y. The derivative of minus square root of y is minus 1/2 times y to the power of minus 1/2. And then the absolute value transforms that minus into a plus, and we end up with exactly what we have here on the right side. So the way we've solved this problem is by finding the CDF of the random variable y, where we had to figure out the interval on which x squared is less than or equal to y, and then we had to find the PDF of y as the derivative of the CDF. But this formula says that a much more direct approach would have been the following. Partition the support of the random variable x into pieces such that the function g of x is strictly monotone on each piece. So we would have partitioned it the way we have, into two pieces, from minus infinity to 0 and from 0 to positive infinity. And then it says apply the formula now, which will involve us finding the inverse of the function gx on each of these pieces, and the rest is just plugging into the formula. The authors are stating that this will generally be the case. So if you had the support of x that had to be partitioned into 5 pieces, because the function g of x is only then strictly monotone on each of these 5 pieces, then in the end the PDF of y will consist of a sum of 5 pieces, and on each of these pieces we're essentially applying the change of variables formula that we've seen before. Pretty cool. We are finally ready to look at a result that I consider to be quite incredible, a result known as the probability integral transform. Before we do that, let's just take one quick second to remind ourselves what it means for a random variable to have the standard uniform distribution. If we had a random variable y with a continuous random variable y with a standard uniform distribution, that means that we'd have the PDF of 1 on the interval from 0 to 1. And we could then get its CDF as well. CDF of y would be the integral of the PDF from minus infinity to lowercase y. Let's quickly point out that y is doing double duty here. What I underlined in orange is a particular place where the CDF is evaluated, whereas the y's underlined with yellow are dummy variables that just go over the interval from negative infinity to that orange y at the top. So to keep things a little cleaner, let's just rename our orange y to a t, and then the lower bound doesn't need to be negative infinity because the support here goes from 0 to 1, So the lower bound is effectively 0. And then we are ready to evaluate this. So the integral from 0 to t of the PDF, which is just 1 dy, is equal to y evaluated at 0 and t, and that is just t minus 0, and that's just t. So if y has the continuous uniform distribution, then its CDF is just y. So, and if we encounter such a CDF crossing the street, we see a CDF of random variable y equaling y, we know that it is the CDF of a standard uniform random variable. Our usual setup has been that we have a random variable x with a certain CDF, and then we form a random variable y by applying some function g to that random variable x, and then we were trying to find the CDF of the random variable y. Now what if we picked for our function g the CDF of the random variable x? The CDF of the random variable x is a function of that lower case x, right? It's a special kind of function, and in this case, let's assume that this CDF is strictly increasing. This will be the case almost always. And if you want to see what happens if the CDF is allowed to have a flat region, the book covers the case when the CDF is not strictly increasing, but is just non-decreasing. But we'll just do the case when the CDF is strictly increasing. Okay, so this might seem strange because we're going to form random variable y by applying the CDF of x to the random variable x. So effectively, the random variable y we're interested in is g of capital X, which is the CDF of x applied to the random variable x. Okay, and now we want to find the CDF of this random variable y. So let's proceed as usual. The CDF of the random variable y is the probability that capital Y is less than or equal to lowercase y. Now let's replace capital Y with its expression in terms of x. Now recall that we're working with the case where the CDF of x is strictly increasing. If the CDF of x is strictly increasing, then its inverse is also strictly increasing. And we can apply the inverse to both sides here. And we know that the inverse, because it's strictly increasing, will be order preserving. So let's see what we get. The probability of, we're going to apply the inverse function to the left side. Then the sign is preserved because the inverse function is strictly increasing. And then on the right side we have the inverse evaluated at lowercase y. Okay, but then what do we have on the left side? Again, no surprise, by design these two will cancel out, right? Because the random variable capital X travels from the range of x to the range of y and then travels right back. And so all we have here on the left is just x less than or equal than the inverse CDF of x evaluated at y. But notice that this is nothing other than the CDF of x evaluated at this point here, which is the inverse of the CDF evaluated at y. And we have one more cancellation here, because now this lowercase y will travel from the range of the random variable y to the range of random variable x and back. And so this is just y. But notice what we just got. We got the fact that the CDF of this random variable y is just y. And recall that we said that if we see such a CDF crossing the street, we'll recognize it as the CDF of a continuous standard uniform random variable. This really asks for a little bit of time for it to sink in, but notice that we didn't say anything about the distribution of the random variable x, but after plugging x into its own CDF, we get a random variable y that always has the standard uniform distribution, no matter what the distribution of the random variable x was to begin with. That's pretty cool. Notice that all the magic here is in the fact that we picked for g of x the CDF function. So the magic here resides with the CDF. Therefore, the probability integral transform can be thought of as a property of a CDF. This is what it does. It can take a variable with any distribution and it will output a standard uniform random variable. Now here's a slightly more visual and more intuitive explanation of the probability integral transform.
Can you tell which remarkable property of the CDF is on display in this image? Let me give you a hint. In each plot, in the bottom right in blue is a PDF, and right above it in orange is the corresponding CDF. Let's see it in action. Let's sample a random variable x from the normal 2-2 PDF. And then let's form another random variable y by plugging x into its own CDF. Now here's the remarkable result. This random variable y will have the standard uniform distribution. Perfectly standard, perfectly uniform. As if we simply sampled it from the boring uniform 0-1 distribution. But we know that our standard uniform random variable y had quite a journey. It was born in the normal 2-2 distribution and then put through a mind-bending transformation via the CDF, and then by some sheer magic we ended up with a standard uniform distributed random variable. But the ever more remarkable fact is that this result holds no matter what distribution we pick for x. This is nothing short of incredible. Let's look at why, if a random variable x has the standard normal distribution, then the random variable y, obtained by plugging x into its own CDF, will have the standard uniform distribution. Picture two equal width x intervals, one near the center of the normal, call it yellow, and one out in the tail, call it purple. Now imagine that we sample millions of random variables from this standard normal distribution, and we are observing this sampling process as it unfolds. Because the PDF is much taller in the yellow region than in the purple region, we'll sample random variables in the yellow region much more often than in the purple region. Where the PDF is tall, the CDF is steep. Where the PDF is short, the CDF is flat. So the random variables that originate in the purple region, and there are fewer of these, right? They get compressed into a much narrower span of y values than the more frequent random variables that originate in the yellow region, and are stretched into a much wider span of y values. This stretching of high-density regions and compression of low-density regions is what equalizes everything and produces a uniform 0-1 distribution.
Up to this point, we have lived in this theoretical world where we have this random variable x with a known distribution, and we want to form another random variable y as a deterministic function of the random variable x, and we're interested in finding out the distribution of this random variable y. But you might ask yourself, in practice, when is it that we want to create such random variables y that are deterministic functions of another random variable? And to answer that, I put together a case study on Artemis 2. On April 1st, 2026, at 22:35:06 UTC, Artemis 2 lifted off from the Kennedy Space Center in Florida, with NASA's SLS rocket carrying Orion and 4 astronauts towards the moon. But let us rewind a bit. In the hours leading up to the liftoff, one number mattered a great deal: temperature at launch time. Too hot or too cold, and the launch could be scrubbed. Too far from forecast, and key assumptions would need to be revisited quickly. Temperature at the time of liftoff was one random variable NASA studied carefully in the days before launch. So we'll briefly go back in time, exactly 24 hours before liftoff, and put ourselves in the shoes of the 4 astronauts, who naturally love probability and want to think probabilistically about a few matters of great importance to the Artemis 2 mission. The temperature at launch time is a random variable which we called f here, and suppose that as of 24 hours before launch, our forecast is that our random variable f will be normally distributed with a mean of 68 and a variance of 16. So f is our key random variable here. Now, each of the 4 astronauts is interested in a random variable that is a deterministic function of this random variable f. And while we know the distribution of f, we do not know the distribution of the 4 random variables that the astronauts are interested in. But fortunately, we just learned how to do that. We learned how to derive the distribution of a random variable that is a deterministic function of another random variable. So you have all you need to derive the distributions of these 4 random variables that the 4 astronauts are interested in. I will leave it to you to work through this case study, and feel free to post questions if you have any. Thanks for watching, and I'll see you in the next video.
prepare to go out of radio communication. To all of you down there on Earth and around Earth, we love you from the moon.